Okay, okay, it's recording now. So anyone just joining us is going to be able to just pause the video and.
A pseudocard. They're a false fruit. What?
Strawberries are false.
Yeah.
You said they weren't berries.
Yeah. They're a false fruit, which is a type of fruit, apparently.
Yeah, there's one.
Okay, there we go.
Okay.
Is corn a false fruit?
Actually, no, corn's not a fruit.
Bro's just making
It's a
things up.
grain, yes.
But like,
So it isn't a fruit.
No,
It's a
barley.
vegetable.
Barley are inside of the flesh.
Yeah.
Is wheat.
Okay, let's do this. Now that our friends who can be here have joined us. Wait, is anyone who isn't here? 1, 2, 3, 4, 5. Oh yeah, we got Corey. What's wrong with him? Okay, so at least one person's not here. Let's see. So 10 cosine of 3t minus 10 sine of 3t. Okay, finally I got my derivative. And I did the product rule here. I factored out the e to the negative 1/2 t, and then did the product rule there. Whew. X prime of 0 is negative 1/2 times negative 4/3 plus, let's see, that's going to be, that's going to be something ugly. We're doing the cosine is the one that's non-zero. So plus radical 47/2 times C2 plus 10. Okay, so this all has to equal 0. And then, what's that? Oh, I did the derivative and used the chain rule. Yeah. Anyway, let's see, can I finish this ever? This is going to be 2/3 plus radical 47/2 C2 plus 10 equals 0. Almost there. Hey, welcome. So radical 47 over 2 C2 is equal to negative, hold on a minute, 32 thirds. So C2 is 16, negative 16 over 3 radical 47. Whew. Yeah, it's pretty ugly. Yeah, it's that radical 47 that is making me so angry. But here's the final answer if you really want to see it. It's going to be this, just a sec. Let me copy this. Put this back up there. We've got some stray parentheses. Okay, so we've got that. And what happened? C2. C2 is what happened. I'll get rid of the C2. I'll make some room. And then we'll just do this. There you go. So that's what, did that explain at all what you were looking for? So yeah, you take the initial conditions, and hopefully the others weren't quite so painful as this one, maybe? Still ugly? But anyway, you take those initial conditions and you pump them into the general solution to figure out what your constants of integration are. So can we do this? What do you think? No?
What?
I told you no.
Wow.
No. Really? No.
We should do it easier for the homework. We don't get so.
We do like a together quiz.
What a great idea. Yeah, it's Friday. And I'm just about, I've lost a couple of, that's enough to send me over the edge.
I know.
I go in the hallway and talk. It's March with Matt.
Oh, yeah, yeah. You know what, dude?
Okay.
Yeah, you guys he doesn't want to, so he's going away. Oh, better bet. I do. I have several. Why? Do you want to borrow it for something?
No. I had a substitute teacher in high school who wore a tie, and I figured,
Xavier, coming back.
Why?
That's good. Come on.
Wait, we're not supposed to be watching TV. Okay, during the quiz, maybe. I'm sorry, your substitute teacher? You're equating me with your substitute teacher?
What's wrong with substitute teachers?
No, I'm just kidding. Wait, have you seen Key and Peele's substitute teacher sketch? That's my favorite.
Why did you say that? It's always
Thank you. Yeah, he had a huge collection of ties. So
Nice.
every time you see him, he had something. Mr. Braley.
Okay, I'll keep that in mind. Yeah, feel free to get help. You're working together? Oh, well then you guys both need to go and get help from Travis. Yeah, see if it's as easy as 27. I'll put this up here. Oh, so you're cutting.
We're gonna get into the right. Why is it Thursday?
Oh, of course, it's equal to sign.
plug in.
Freeze.
Sheldon, you're missing your part. Oh, sign line. Oh, just missing the C line.
Oh, yeah, it's without finding, yeah, so you have to still find it. Even if you like, you still have to walk that. We don't have to figure not that.
You're already done?
Yeah. Oh.
What? Oh, you didn't see part C?
No. But that doesn't really change anything. You do, but the B eats it.
The B eats it.
Yeah. The B is just, we don't care what it is yet. So.
You're consuming your constants?
Yeah. You're supposed to. If you don't, there's less.
Not in this case.
Really? The 5?
I don't know where you're doing this consumption, so that's what scares me.
Instead of writing 5B cosine?
It's 5b, because b is a constant, and the derivative is 5 times that constant. Because you're not making a general solution.
Why is it even negative?
It doesn't.
Whoa.
Doesn't need anything.
Uh-oh. Last class, it ate something.
No. There was no consumption of constants in last class. Well, not in this context.
Okay.
It was in a different context.
Uh-oh. Failed.
Yeah, I think we need a full sheet, not a half sheet.
I'll take that under advisement. Thank you.
I'm actually just, is it okay if I like look for the back of this?
Oh, yeah. No, that's for later. That's the ruling the slide. He's already got it. I just wanted to make sure you had the opportunity, if you chose, to play with it.
Is this part of mathematics?
No, it's part of Laplace transforms.
That basically, they're getting dubs. 11. Is it right? I'm pretty sure that's right.
So when we're writing this part, we put a 5 here.
Yeah.
Okay.
I know. You get so used to eating up those constants.
Well, I feel like I don't
Chomp
know.
chomp. Delicious.
Okay.
What the heck?
But no, that is what's the derivative of
Cosine. Hey, let's just do part A and even just set up part B. I'll explain in a minute, but if you can do part A, I think you get a star. Or wait, general solution. Yeah, yeah, do part B or part 2B. No, 2A. 2A, which is just the homogeneous part of the solution. I'll show you why in a minute, but I got to finish typing just a sec. Wait, did I win? Did I win? Is that what's here? I'll show you. Here's my bracket. Oh, it's not up there. Why is it not up there? Unfreeze. Here we go. See, did I win? Oh, look. I've got 13 points.
Connor's demolishing.
Is that good?
Oh, not really.
Well, you're in
He's
third
still doing
place.
good.
Hey, I'm right there. I'm tied for third.
Wait, who's at the top?
Connor.
Let's go, Connor.
I think it's fixed. I think it's fixed because last year Dr. Brad won.
Dr. Brad was the one who picked Kansas last year. Someone picked Texas A&M up there. Who picked Texas A&M?
Look,
I'm tied for second in mine.
Yeah, look who I picked. I picked UNC Chapel Hill. See? Oh.
I don't know if that was a good pick,
All right. I did my best. Okay, well, we should actually do some work because we have people walking by looking in and thinking, what are they doing?
We're doing statistics.
Okay. Okay, so yeah, let's see what's going on here. Where's my so you remember how I just a few seconds ago I mentioned that it's hard to come up with a problem that works out nicely? Just bear that in mind. So it started out, I was like, oh, this is great, right? You got to this stage? Everyone was happy at this point, right? This is happy times. But then you get down here and you're like, okay, what's going on? And let me show you how far I went before I gave up.
Oh my gosh.
Once I saw this, I was like, oh, this isn't going to be nice. And so I went to the computer. I'll show you. This is the final answer after plugging in doing part 3. So let me show you the final answer after part 3. Give me a sec. Pull this over. There he is. So you get 25 over 1972 times cosine of 5t minus 19 over 1972 sine of 5t plus, yeah, it's just not worth it. Hold on a minute. Oh, here's what I did. Sorry. I skipped a step up here that you didn't see. So in the original, it was 2, 10, 12, and 1. I divided everything by 2. So I got 1, 5, 6, and this is 1/2 now. And so down here, well, this one's 1/2, and this one's 0. Yeah. So yeah, and then yeah, like I said, I gave up. Yeah.
Can you scroll up a little bit?
To the stuff that you could actually do.
Okay.
No, I'm just kidding. No. I totally am there with you.
X particular. That's what I was asking. The B8, the 5.
What are you talking about?
X particular, not the derivative of it. That one.
What?
That's when you go to write it, the derivative of sine of 5t.
Oh, I get what he's saying. Okay, because we got the cosine because cosine is the derivative of sine, right? So I think
My question was, is the b eating the derivative? Like the derivative of sine of 5t should have been 5 cosine.
Yeah, here it is, 5.
yes, but no. Just staying in the x particular. What you used to find
Oh,
that second
yes,
Oh,
part.
yes.
there. Okay.
Yes.
Yes.
Okay. I'm so upset.
I'm sorry. I misunderstood. I
Mine
thought
is
you.
so much
I thought
bigger.
you were absorbing this one.
Uh-huh.
That one was the one I thought you were absorbing. I mean, it'll work if you put the 5 here. This would be 25, 125.
Yeah, it
But-
is.
Okay, so yeah, this is how I feel as well. So let's just move on to slide rules to see what this is all about. Slide rules, they were invented, let's see, when was it? Maybe 1400, somewhere in that range. They are a tool for computing numbers, and they are based on the logarithm, which is a tool or an idea that a guy by the name of John Napier he discovered. He didn't invent them, but he discovered that you could use these to help compute things for in scientific calculations. So I don't know which is better, this or that. Okay, so here's the deal. A slide rule is just a logarithmic scale. I know there's a whole bunch of slides or there's a whole bunch of rules there, but the ones that are important, that's these two right here, A and B on mine. They're just the two that you have there if you choose to cut this thing out. Anyway, the A and the B, those are the important ones. The rest of these, all of these, this is trigonometric. I think that's tangent, sine, cosine, I don't know. But there's other scales down here, but the ones that are from the OG scales, from the original slide rules were A and B. And so those are the ones we're going to use. And so here's how you use a slide rule. First of all, I have to show you how you're going to use logarithms. So let's just switch back to logarithmic. Where is my logarithms? Hold on a sec. There it is. So why? Why would we care about logarithms and slide rules? Well, it's because of the, there. So why would we care? It's because of this, that real numbers and logarithms of real numbers can easily, you can go back and forth between the two because you know what a logarithm is. So for example, the logarithm of 1 is 0 and e to the 0 is 1. So there's this transformation. In the olden days, back before you had a hand calculator, people had tables of logarithms. Keep us updated.
Yep, it's coming around the wire here.
I can't wait to update my March Madness thing because I want to see myself jump up to the top.
And middle.
Excellent.
Favorable.
Oh, is that good or bad?
Most likely.
Like there's
Yes.
How quickly does this thing update? Okay, we'll do it later. So maybe before the end, I'll check again. Wait, what are you doing? Are you watching a video game?
Am I watching a video?
Okay, well here's the deal. Let's just let's try to survive these next couple of minutes together. So real numbers, logarithms of real numbers can be easily switched between the two of them. And so what happens though is when you switch to logarithm land, multiplications become additions, and division becomes subtraction, and exponentiation becomes multiplication. So for example, if I have A times B, and I want to do that operation, I could do the log of A times B, and that's going to be the same as the log of A plus the log of B. And addition is easier than multiplication. And so what Napier would do is he would have his computers, which were people at the time because we didn't have real computers or digital computers, and he would have them use logarithms to simplify their calculations. Instead of multiplying two big numbers, you compute the logs of those two big numbers and then add those numbers and then unlog them. And he had a series of tables to do this. This slide rule and the things that you have in front of you do the same thing. So let me just show you how this works. the way you do this, if you want to multiply two numbers together, the first thing you do is, let's just take the numbers, how about 2 times 5? No, that's too easy. 2 times 4, a little harder, right? 2 times 4. What you do is you find the 2 on the A scale, that's the top scale, and it happens to be right here. And I'm going to put the 1 from the, so you have the 2 on the A scale, it's right above the 1 on the B scale. And then you move your little slide. I know you don't have a slide, sorry. You move your slide over so that it is on top of the 4. Let's see, can I do this here without grossing you out with my fat finger? Okay, there it is. And notice that right above the 4 is 8. 2 times 4 is 8. In fact, they're all lined up perfectly. 2, well, not perfectly because this isn't lined up perfectly, but 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 1. Okay, it's 10. But you get the picture. It's that you can multiply two numbers by lining them up on this. You can do a similar thing by lining up two numbers that you want to divide. Let's say I want to do, how about 16 divided by 3? So give me a sec here. I actually have to use glasses to see this thing. So 16 divided by 3, I find 16. Give me a sec. I'll find it here. Let's see, 1, 2, 3, 4, 5, 6. So it's right here. I'll show you my little, the slide is right on top of it. So you actually have to go, this is 10, and then 11, 12, 13, 14, 15, 16. It's that long line there. And I wanted to divide that by 3. So I'll move the bottom slide over to 3. There we go. So 16 divided by 3 will be actually right where the 1 is, right there. So that's what, 5.3 and a little bit more. Isn't that cool? So you can do division, multiplication. We could do exponentiation. I think we have to use a different slide for the exponentiation. But that's the basis for a slide rule. Slide rules take arithmetic problems and make them easier by turning the arithmetic problems into simpler things like this. We're going to do the same thing with Laplace transforms. You might wonder why. Why do we do Laplace transforms? Well, here's why. You have ordinary differential equations, and that's going to be our, in our normal universe here. And what we're going to do is we're going to bend time and space, literally. That's what a Laplace transform does, is it takes time and it changes it and exchanges it for space. Time and space, they're kind of interchangeable if you believe Einstein. But anyway, so we take those ordinary differential equations and you transform them into a different universe, the universe of Laplace transforms. Now, in the ordinary differential equation land, you have integration. But the transform takes integration and it turns it into basic algebra. Sometimes difficult basic algebra, but it's basic algebra nonetheless. So you take integration problems and turn them into algebra problems. You take solving for constants and that just plug in the initial condition. So you don't have to, all the work that we just did for this problem that we just tried to do, it would be trivial actually when you use Laplace transforms. And then knowing lots of integration techniques. Let's say that you don't know very much, about integration, like integration by parts. What's that? I have no idea. Well, fortunately for us, you can look up most of this stuff in a table. So I'll give you a table. In fact, on the next exam and on the final, I will have a table. We're going to work on that table together Monday because of March Madness apparently. But on Monday, we'll start making that table where we have a table of Laplace transforms and it will be the dictionary. You'll look up a function and you'll say, Laplace transform is this. In fact, just as an example, I'll tell you right now that, here, I'll put this up here. Let's see. Yeah, I don't want to reveal all of this, all these goodies. But here, just as an example, in ordinary differential equation land, you might have this function. Let's do this, e to the t. Let's just do that. So e to the t in normal ordinary differential equation land, that thing becomes over here. So that's ordinary differential equations. When you transform it, it becomes 1 over s minus 1. That's the sort of thing we're going to take these things that we're used to, transform them into this new universe. And you can think of it in this way, that this is time, t. Time is the important variable. And when you transform something using a Laplace transform, space or distance or arc length becomes the important variable. Just to show you that I know how to do this, we could also do sine of t. When it goes through the transformation process, it becomes 1 over 1 plus t squared. So sine of t gets transformed. You might notice, oh, I'm sorry, I blew it. Let's try this again. S squared. There, that's better because we have time on the left, space on the right. So here's the big idea is we're going to take our ordinary differential equations, do the transformation of them, kind of like a person from the 1940s or 50s using a slide rule to take all of the arithmetic that they were doing and pump it into logarithms. So you change everything to transforms, solve the problem algebraically, and that'll become more clear on Monday. I know we're not going to be able to do it all today, but solve that problem algebraically and then go back. So then if your answer over here was this, you could say, oh, I know what the answer is in this land, is they go back and forth. You can go back and forth with these Laplace transforms. All right, so we've bent time streams in the desert. Okay, so I discovered, was it in here that people were complaining that I should just have all of my videos be public? Every single class has denied this. One of my classes, I think it was Calculus 2, one of them was saying, why don't you just make all your videos public? Then you won't have to go through the trouble of adding them to the, then we could just subscribe to your channel and pick out the ones that I want to see. Well, I didn't want to do that because I have my personal YouTube channel, which has just a few videos of my kids playing their strings or whatever. But I found a way. I actually have a second channel now. So I will have that up and running on, it's actually up and running now, it just has nothing in it. I have to get a few more things set up. It will be ready on Monday so that on Monday I'll have a link to it and you can subscribe and like. That way I can start monetizing. No, I don't, but it'll all be public on that channel so that you can just sort through. I'll show you what I mean when we get to Monday, so you can see that. All right, so homework. Apparently, homework is deferred. You know what? I hear your cries for rest and recuperation, and I sympathize. I need some rest and recuperation. I need to find another cufflink, apparently. So we will rest this weekend. Get caught up in your dynamics, fluid dynamics, whatever it is. You have homework for me, though. So you can just either leave the scissors where you have them or make a little pile up here on Clayton's desk. That'd be fine, too. Don't hurt him, though. No, keep the quiz as a souvenir of how badly I wrote that problem. I thought it looks so innocuous, doesn't it?
Yeah.
Something went wrong. Because I didn't mean for those fractions to be so nasty. All right, I gotta check. Let's check the madness now. I'll stop my stream, then we'll check. Baby's gonna get upset. See? Oh, I'm still in the same place. Does it not update? It didn't update. Where is this Xavier thing?
It's right there. You pick on the win.
Oh, you had errors.
Oh, I win. Wait, that was good?
Yeah.
Wait, they weren't supposed to win?
No, Kennesaw State, I chose to win in every single bracket.
Oh, so now you're a big loser.
Yeah, like Kennesaw State.
Okay. All right. Well, I thought that something exciting would happen, but apparently not. All right. Enjoy your weekend. Take a rest. Take a break.
That sounds good.
Yeah, pizza party Friday night. That's my family. It's pizza party Friday night every Friday.
Yeah.
Okay. Pizza. Oh, you got goodies for me? Thank you.
Yep, I gave you both of them.
All right, it's like the door
Yep, thank you.
restaurant, like cheese place.
No, like what do you get on it?
Oh, I love cheese. Hey, you can have.
This is like cheese pizza.
I love cheese pizza. I like no cheese, no sauce.
No
just like
bread. You just want the pepperoni? How are you holding up, Sam?
I'm doing pretty good.
All right, I'm, oh.